Alright, so in this video, we're going to pick up kind of where we left off last night. We talked about sample space, we talked about probability of events, we talked about independent and dependent events last night, along with some counting techniques. First thing I want to talk about is let's talk about conditional events or conditional probability. The idea of conditional probability is something that's already happened now. Something's already happened. Okay, so listen, you got up late for work. What's the probability that you got up late? I'm sorry. What's the probability that you're late for work now? It's probably a lot higher than if you'd gotten up on time. You silly goose. Okay. What? Yeah. So you decided to drop out of high school. Oh. So does that change your probability of becoming a successful lawyer? Probably. So in other words, something that you did affects something else. But notice, it's not the same as just saying dependent probability. So, for instance, let's say a kid goes into high school, 85% chance he graduates, and a 15% chance he drops out. Okay, cool, whatever. Nice. Now, if you're a graduate and you want to become a lawyer, I don't know. Let's say you want to become a lawyer. There's a 30% chance you make it. Okay, cool, nice. And a 70% chance you don't. What does that mean? Does that mean you applied for law school? I don't really know. I'm just making up a number here. Are you with me? So maybe 5% of everybody that graduates from high school becomes a lawyer. I don't know. I'm just saying that apparently you decided you want to be a lawyer and you applied. Maybe you got turned down. Maybe you got into school and you washed out. Maybe you got into school, you realized, it's not for me. Whatever it happens to be. Okay? But let's say you're a high school dropout. Then you go, all right, so I finally get my GED 10 years later. Okay, cool. Now I want to be a lawyer. Boom. Boom. Cool. So what is the probability that you are I can say a high school graduate and a lawyer? So we talked about last time. Wait, I heard and. Well, of course, it's 85% times 30%. And so obviously those things went together. But here's the question. What's the probability that you end up being a lawyer? Well, what do you mean, Jay? Well, I mean, you're a kid, you're a freshman in high school. What's the probability you end up being a lawyer? Well, there's two things that can happen. Either this or, so plus this. That's the probability you end up being a lawyer before anything happens. Okay, this is before anything happens. Anything goes, anything goes. A lot of things can happen. How about that? A lot of things could happen. And so let's just see what that busts out to real quick. So 0.85 times 0.3 is 0.255. And then, of course, the second one's going to be a skosh bigger because we're going to add 0.15 times 0.05. Somewhere, some idiot forgot a decimal place. Let's try that again, Jay. So 0.15 times 0.05. Nice. Plus 0.255. Nice. So about 26% chance that you become a lawyer, like say when you're still in high school, okay, before anything happens. Okay. Now you could argue that, well, listen, I failed all my classes freshman year, so I'm more likely to be a dropout. Yeah, exactly. This goes on forever and ever and ever, right? There's really this is arbitrary things we're cutting off here. But let's just say this. Wait, I'm a high school dropout. What's the probability to become a lawyer? I don't want to say that. Oh, this is how we statistics people say it. What's probably to become a lawyer given I drop out of high school? Oh no. What had to happen first? You had to drop out. So because I dropped out, there's only a 5% chance that I become a lawyer. Okay? Well, what about the fact that I could have graduated from high school? You could have, but you didn't, see? You already did something. Okay? Now, we do this kind of stuff all the time. Okay? So we'll talk about things like this. Let's say you work in in some sort of manufacturing process. Hey, what percent of defective what percent? Let me try it again, Jay. What percent of day shifts items are defective? What does that mean? Well, it means I'm only interested in the day shift. But what about night shift? What about them? I only want to know about day shift. So we could say this as another way of saying this would be the probability that the thing is defective given it was from the day shift. We could say like things like this. What percent of juniors play football? I don't know, but I'd probably go look it up somewhere. So it's the probability the kid plays football given they're a junior. Boom, done. These are equivalent statements. We frequently say it this way in the real world because you sound goofy saying, what's probability is this given that? Okay, but they mean the exact same thing. Okay. Now, one of my classic moments of all time, although I'll be honest with you, just drop down the list of weirdest things that's ever happened to me because of something that happened earlier this week, which I'm not at liberty to talk about right now, but let me tell you, wow. I mean, wow. But several years ago, it was actually, I think, in 2008, as I recall, I read this study. I just read it online. It was done by the CDC. You can read the article. It's still online. For those of you that wonder, there probably is data about males as well, but females tend to have more. Typically, they get this information from the doctors. It wasn't like you brought necessarily people in off the street. So you gather data from people going to the doctor and having random exams done. I should say it that way, I guess. And so this statistic came out. I thought it was interesting one night when I read it before class one day. Well, actually, it was one morning. One morning before my stats class at the high school, I read this. It said 1 in 4 teen girls have at least one STD. And you're like, interesting. Further, 1 in 2 are active. And so what I did was I went to the board and I drew this picture. And I wish I was there to watch your faces right now. And everyone's like, oh, that's right, Jay. Nice job. You did 50% correctly. Thank you. Boom. STD. Non-STD. It's at this juncture someone usually, after a few minutes, I write down the board and people kind of go, what are you doing, crackhead? Like, what do you mean? Well, like, you're saying that you're just as likely to get an STD if you're non-active as if you're active. Wait, so? Well, I don't feel like that's right. Well, why not? It feels like you should be more likely to do something if something else has happened already. Oh, I see. And so what you're basically going to end up happening is this. This is 25% or 1 in 4 of all girls. This is 1/2 of all girls. My question to you is this. What's the probability that the person has an STD given that they were active? This is based on this study's data. I am passing no judgment. I am making no claims other than that was the study. If you giggle it, literally 1 in 14 girls, CDC study, blah, blah, blah. There it is. 2008, as I recall. Okay. Now, again, whatever. This is just a cool way of doing this. You're like, wait, Jay, again, it would not make sense if it was this way. What do you mean it wouldn't make sense? It wouldn't make sense because then whether you're active or not has no impact on whether you have an STD. And that's literally the definition of an STD. You kind of got to be active first. Typically, although, yes, there's always the exception. They're born with it, got blood transfusion, et cetera, et cetera, et cetera. Even if there were a few on the non-active side, relatively few, percentage-wise, it is nowhere near the same on the other side. If it was, we would say they were independent events. And as a result, we wouldn't call them STDs. We'd just call them TDs. For instance, when you look at the COVIDs is not transmitted sexually. At least we don't think it is. It is respiratory. Therefore, it has no impact on what you were doing, you know. It is a respiratory disease. Now, if you are in close proximity to someone, well, then of course you can share it, but it's a respiratory condition that you're going to get it from. Okay? Now, clearly, back in the 80s, when AIDS first became a thing, they didn't initially know how it was being transmitted. And people were freaked out. As a person who lived through the 80s, well, I was in high school in the 80s, a little weird. Like, where's it come from? You gonna catch it off the toilet? Oh, if you eat off a fork off of somebody? Ooh. Yeah, but it was washed and sterilized. Yeah, but ooh, we didn't know. Okay. And so finally, when they pinned it down to, oh, there's why. Oh, okay. Well, then I guess if you're not active with a gazillion partners and you're safe, whatever, then you're probably fine. And if you're not, well, then there you go. Okay. So again, it is different. This probability that you have an STD given you're active, well, it's 25% of everybody over 50%. In other words, it's 1/2 or 50% chance that you have an STD if you're on the active side. Is that the same as you have on the other side? And the answer, of course, is no, it's not the same. Now, it doesn't necessarily mean this one's 0. In fact, this one might be, I'm just going to make up a number, 1%. It could be 1%. But you notice that these are not equal. If they were, that would suggest that those things, that is, active and STD, it would suggest that they were independent. They're not independent because they're wildly different from one another. Okay? So conditional probability is actually kind of a neat thing. Now, look at this right here for a minute. This 25%, what is that? This is the probability that you are active and STD. Well, not you, I'm just saying. And then what had to happen first? Well, on the bottom, it was probability of active only. Now, the reason I still like to use this is because it's one of those surreal moments, okay? Kids are just like, whoa, whoa. And there were some other fun times, but whatever. It's kind of hard to describe on video in class. It's a little more fun. But now, so what we say is the probability of B given A is equal to the probability of A and B over the probability that A had already happened. So in the case of our lawyer thing before, okay, in the case of our lawyer thing, you're like, wait, what happened now on that? Now think about this for a minute. In our lawyer situation, the probability that you are a lawyer, given that you are a dropout, let's think about this for a minute. Now, we already kind of told you some of the ideas here, but when we start looking at actual data, we're not going to be told the 5% and the 85% and all that good garbage. We're going to be getting this from data. We're going to be collecting that data and using it that way. But we know this. This was 0.2. No, it wasn't. That was the wrong one, stupid. I don't know that I figured the other one out. Let's go back and look at that picture over there. Yes, there we go. So given that you're a dropout, well, that'd be 15% of 5%, which I never truly added together, did I? Let's break out a calculator. .0075. 0.0075 out of 15%. Right? That is, you had to be a dropout first. Divided by 15%, and lo and behold, there's your 5%. Now, again, we knew this going in, so this is goofy to do it that way. But what we're going to see today is things like, hey, here's a set of data. There's this many kids that do whatever, and there's this many kids that do whatever. And so, what's probably the kid does this, given that they do that too. And we'll look at some data to see how that works out. So it's a lot of fun. It's not very hard to do. It's almost fun. Classic example, another classic example. In a particular town, let's say 5% of all cars are stolen in a given year, or whatever you want to call it. I don't care. It doesn't matter. Check this out. 70% of stolen cars are found. No. Hold on. Back the train up. Back the train up. I got you. 3.5% of all cars are found after they were stolen. What's the probability the police solves your case? In other words, what's the probability that they find your car, given that it was stolen? Again, they're not really looking for your car if it wasn't stolen. That's kind of ridiculous. And so there'd be 3.5% out of 5%, which is 70%. In other words, the cops only find 70% of these cars after they're stolen. Why aren't they looking for your car? Because it wasn't stolen, silly goose. Okay, they're only looking for stolen vehicles. Okay, now in certain towns, maybe the cops, I don't know, there's not as good at chop shops, whatever. The cops maybe are on more, a little more on the ball. Whatever the case, you might have a higher percentage of finding. In other words, you might do it at 90%. That means you would find 4.5% of all cars that you might find 4.5% of all cars that have been. Try again, Jay. In that town, 4.5% of all cars would have been stolen and found, meaning that you'd have found 90% of the ones that were stolen. That's the idea of it. Okay. Now, when you bust through these things, it's not very difficult. Now, a cop, you're like, here I am at the database at the police station going through stuff. Hey, not surprisingly, I'm only looking for cars that are stolen. Let's say that there was 1,000 cars stolen this year. All right. And we found 920 of them. Bitching. That's 92%. Nice. That's us. This is the probability that they were found, given that they were stolen. But Jay, you didn't take into consideration the rest of the cars. I don't have to. I'm only interested in the ones that have been stolen. Okay? If you are in charge of the day shift, I don't care about night shift, bud. Let's work about us and work about our day shift stuff. Let's do our thing. Okay? Oh, you manage the Taco Bell. Okay, well, whatever. But what about the Arby's? What about them? Do your own thing, sir. Focus on your own deal. That's what conditional probability is all about. Okay? So it's kind of fun. It's almost a good time. And so I want to talk to you about this. Now I'm going to pull up a data sheet. I'm going to pause you momentarily. Whilst I pull it up. Oop, what just happened? Okay, so this should look vaguely familiar because literally it's the same kind of data. I'm not sure if it's the exact one, but it's very similar. Why? Because I can. I don't know what to tell you, bud. Just some random data sets. Doesn't really make any difference to me which one we use. Boom. Now I'm going to do insert a pivot table, and I'm going to answer a few questions here. Okay. Why are you doing it this way, Jay? Well, because I'm going to ask some questions. So if I asked you, hey, what's the probability that a kid lives with mom? I don't know. Let's find out. So, probability that a kid lives with mom. We have some people in our hat. The question is, who's in the hat? So when I'm phrasing these questions, the thing to remember is, who's in your hat? In other words, who's your denominator? Okay? Who is in the hat? Okay, because that'll always be your denominator, right? In this case, it doesn't specify, so it's everyone. Everyone. So if you go look at Excel over here, you're like, oh, sweet. Let's do lives with parents. Maybe. Come on, come. Oh, go with me now. Come on, move. Worthless hippie. This is hard to do with the old tablet. There you go. Kid. There's 300 kids and 95 of them live with mama. Ta-da! Piece of cake. Cool. Let's do another one. Awesome. Hey, what's the probability that the kid lives with mom and not dad, that's boring. And I can't remember what the other categories are. And likes broccoli. Oh, who's it out of? Well, I feel like it's everyone, which means that 300 is my denominator. So on this one, I feel like I should just drag down favorite vegetable. Oh, shoot. You worthless pig, get back over there. Favorite vegetable. Nice. Broccoli, mama, bam. There are 27 of them out of 300. You're like, Cool. Awesome. Okay, I guess. Okay, well, that's exciting. Okay, what percent of corn lovers drive I can't remember the other categories. Drive a Chevy. Sure, drive a Chevy. Chevy. I got a Chevy. Nice. Cool. So I don't know. I literally don't know. I'm just going to start over because, well, I can. And I'm going to drink favorite vegetable to here, perhaps. Favorite vegetable to there, perhaps. And you're like, but Jay, is there a better way to do this? Of course, there's a good way and a bad way. There's different ways. Check it out. So, what percent of corn lovers? There are 93 corn lovers. In fact, corn lovers is who's in my hat. In fact, another way to write this problem, which we just saw a few minutes ago, was Chevy given corn. Because corn is who's in my hat. How many corns? 93. So then if you go back and look at the data set, you're like, how many of those are Chevys? 7. 7. Ta-da! Jay, is there a better way to do that problem? I think so. My favorite way to do this problem is instead, what I like to do is I like to filter it by the event A. So in our case, the thing that had to happen first was corn. So I'm going to filter it by corn, which means that I'm going to do brand of car here. Oh, maybe I'm not. Come on. Brand of car, give it to me. Here and here. So there's all of the people. But I'm really only interested in corn people. So check it out. Boom. And now I can filter out just the corn. But what about broccoli? What about it, sir, ma'am? I don't want those people. I only want the corn. And there, check it out. There's 93 corn people, 7 of which drive Chevys. One moment, please. All right. So let's try another one of these ones. They're kind of fun, I think. What's the probability that a person drives a Chevy given that they are blonde or redheads? Nice. Again, this had to happen first. Who's in your hat? These people are in your hat. Nice. So we're going to filter it by that. Okay, cool. Now, that's one way to do it. Another way you say is what percent of blondes and reds drive Chevy. Just another way of saying it, right? That's it. Nothing to it. So if you're doing this, again, I'm going to filter by hair color because that's who I'm interested in what they drive. But I'm only interested in that for certain kinds of people. So yeah, Chevy. Get down there, Chevy. And then hair color. Boop. So let's filter out. Right now it's everybody. Let's just get just the blondes and the redheads. Now you got to click on you click on multiple items, then you can select blonde and red. Click it, dummy. Oh, not bald. That's weird. There you go. Cool. So there are 85 blondes and redheads. That's my denominator. And how many of them drive Chevrolet? Turns out 5 of them do. Nice. Cool. We do this till we're blue in the face, man. Till we're blue in the face. Now, could you have done it a different way? You can always do things a different way, my man. Check it out. Oops, let's unfilter those. Just one moment, please. I forgot I need to unfilter. Give me the unfilter. There we go. Cool. There's everybody. There's 66 blondes. Do you see that right there? And there's 19 reds. That's a grand total of 85. And of them, 4 plus 1, which is 5. 5 out of 85. That's hard to do. So for me, it's easier to bring these guys over here and then filter out the ones I'm interested in. To me, that's just a nicer way to go. Okay? Undo that. Blonde, brown. What are you doing? Bald, etc. Ta-da. And I think that's just an easier way to go. Okay. Now, On the pivot table assignment, you're going to be doing basically this very same thing. But what are you really doing here? What you're really doing is you're going through and you're looking at data and you're finding probabilities. That's all you're doing. Remember, probability, percent, proportion, potato, vodka. It doesn't make any difference. It's a different way of saying it. If I'm asking you, hey, what percent of your things that you made today are defective? Another way of saying that is, hey, put all that crap in a box, reach in and grab one. What's the probability that one of those will be defective? Because it's the same thing. Another way of saying that would be saying, what proportion of them are defective? That's it, the same thing. Now you could say, listen, so today we had day shift and night shift. They both made stuff. So, but I'm only interested in the night shift. So, given that we're talking about night shifts, in other words, what's the proportion? What proportion of our stuff is defective, given it was made by the night shift crew? Okay, that's the thing I'm interested in, and that's where conditional probability shines. Now, the question might be something like this: suppose you're doing a problem and you got this, the probability of the defective, given it was made by the night shift. Suppose it was equal to. What does that tell me? It tells me that the probability of being defective is not dependent on what shift it was making. What does that mean? It means that, man, both of our shifts are great. No, it doesn't. It means they're the same. But what it means is that the defective is not dependent on what shift is made. They could both be equally crappy. They could both be equally good. Okay, but there's no difference between them. Okay, meaning it's independent. Anytime this probability is equal, oh, by the way, if it's truly equal, someone's been screwing with your data. Are you with me? It's never going to be perfectly equal. If it's about the same. So in other words, if about, oh crap, if about, I don't know, 1.9% of my day shift ones were defective, they just made that up, and, oh, I don't know, 2.3% of my night shifts were, or whatever, you're like, oh, that's about the same. Yeah, I would say that, yeah, they're about the same. Therefore, it's independent of it. In other words, there's not, one of them is not necessarily better than the other. Now you can say, well, the one is better than the other. 1.9 is better than 2.3. Yeah. Is it significantly better? And later on this term, we're going to be looking at some tests for that. Not this specific one, but we will be looking at some tests to see, yeah, is there a difference? Is it a significant difference? Now you might look at that and go, that's not significant in my mind. It's only 0.4%, and you might be right, but it's possible that is a significant difference. But just by the eyeball, you're kind of like, yeah, it's about the same. Oh, all right, cool. If it was 19% versus 2.3%, Lord have mercy, your night shift sucks, bud. Shut it down. Figure it out. Fire them all. Get new managers. I don't know. It's bad, bro. It is awful. This is not okay. And therefore, what we're saying is it's dependent. The number of defectives, or the probability that you get defective, is dependent on what shift it came off. That's a problem. Okay. In fact, when you're doing quality control, okay, and you've got two lines making stuff, or let's say here's the U.S. of A. Woo, woo, yay, cool. And you've got a Budweiser plant here and a Budweiser plant here. And I always pick Budweiser because, well, everybody knows it, and everyone's like, oh my gosh, it tastes like swill. You know what it tastes like? It's consistency. Consistency doesn't necessarily taste good. It's consistent. Okay? When you go on vacation, now when you're home, you will go and eat at some little hole-in-the-wall restaurant in your little hometown. Anybody driving through your little hometown looks at that place and goes, dude, that looks like a place where I would go and get, some intestinal issues. When you're on vacation, you will drive through somebody else's hometown. You will drive past some little hole-in-the-wall restaurant and you're like, I need to be on the road for the next 8 days. I cannot afford intestinal troubles. So where do you go? You go to Applebee's. You go to McDonald's. You go to Taco Bell, Burger King, etc. Why? Because they are consistent. Are they consistently good? No. They are consistent. And your little tum-tum, although you're not like, oh, I wish there were those burritos from that little hole-in-the-wall place, or that one place that makes the really good, come on, Jay, use your words, sweet and sour chicken or whatever. You're like, oh, it's the best ever, man. All right. You know those places are hit and miss. You know you could ruin your entire vacation going to those places. So what do? You shoot for consistency. Not consistently good. You go for consistent. The Budweiser that you crack open over here in where is that? Ohio? Nice. Is going to taste exactly the same as this one down here in Phoenix. Exactly the same. There is zero difference. If there was, if you could taste the difference between them, say, that's not cute. That will kill your business faster than anything. Inconsistency kills businesses. If that was not true, McDonald's would have been out of business a million years ago. Here, let's put out an inferior product that kind of tastes like, ugh. And people just buy it up like crazy. Just buy it up like crazy. Hey, we'll call this a milkshake. And you're like, well, what is it? I don't know. I don't know exactly, but I don't think it's a milkshake. And but yeah, look at that, people buying it. All right, right on. They do a nice coffee. I do appreciate their coffee, but other than that, yeah. You like, but what about these other restaurants, dude? They can be hit and miss, right? From day to day, week to week, whatever, to month to month. You just never know. It's not unheard of that you would catch food poisoning in McDonald's, but it's pretty darn unlikely. Because why? Because they do the same thing, and you're selling all those burgers out every day. You're clearing tons of fries every day. Stuff doesn't lay around long enough to get food poisoning. You go to some little hole in the wall establishment. They've got a crock pot full of sweet and sour chicken over there. Yeah, it's been there for a week, but sure, it still looks pretty good. Yeah, great, awesome. We don't do that. Okay, we like consistency. And so this idea that the probability that you get a defective, given it was from Phoenix, or defective, or not as good, or whatever, you would like that better be equal to everywhere else. Or if you want to think of good or whatever you want, it doesn't matter to me. I don't care what you do it. Okay, they better be the same. There better be zero difference, meaning it better be the same regardless of where you're at. Therefore, it is independent. Okay? Now, once in a while, you'll run into something that's similar to that, but I'm going to do it in a little bit different fashion. Okay? Oftentimes, it's kind of fun to look at. Back in the day, I used to ask people, what kind of if I brought up a car, there's certain things that it screams. Okay, so like for instance, in this part of the country, if you see a brand new Porsche driving down the street, it is almost assuredly, and this is how you know, by the way, you would bet money on it, that it's an old man. Okay, your age, Jay? Probably a little older than me, but yeah, probably. Mm-hmm. Would be me? No, I'm not driving one of those glorified VWs. No thanks. Overpriced, glorified VW. Pass. Now, here's the game. Why is it in this part of the country that it's only old men, typically, that drive them? Now, you're like, Jay, that's, I don't know, sexist or ageist or something of you. Hold tight, pal. I got a bet for you. I will bet you $1,000 right now that next Porsche driving down the street is a 16-year-old girl. Oh, I'll take that bet, Jay. What do you mean? Well, of course it's going to be an old guy. Whoa, whoa, whoa. I thought you said that was a problem. Well, well. Yeah, when the money's on the line, you know what the real bet is. Okay? If you'd bet on it, that means your mind understands. You may not agree with yourself, but when the money's on the line, yeah, I'm going to bet on that. Okay? So I'm going to say it's probably an old man. Now, you go to Miami, not so much, right? Why? Because I guess there's probably a lot more money down there. Maybe it's a lot more cooler of a thing, places like that. Maybe they tend to drive at younger ages. Up here, you see old guys driving it. Why? Because they can finally afford it, and they still think they need to show off to somebody, I guess. Okay? I'm not saying that a 35-year-old woman couldn't be driving her kid to school, because that's only not one kid, just one kid at a time, because they can't carry any more than one kid at a time to school. You're certainly welcome to do that. But typically, as a younger person, we're not going to be driving Porsches because A, we can't afford them, and B, they're pretty useless at carrying children around. So there are certain cars that scream certain age brackets, 50 to 60, and maybe I'm going to write 40 to 50-year-olds, and then 30 to 40-year-olds. I don't know why I'm going backwards, but I'm doing it. Screw it, I don't care. We're going in, okay? Probably 0. 1, 2, no, 12, and I don't know, 20. Sweet. I don't know. I just made that up. Don't argue with me. I just made it up. Minivan. Now, if I included my mom and dad, they have one, but they're like in their 70s, whatever. When he bought that thing a few years ago, he was all jazzed up about it. He's like, "Oh, Jay, look at this thing. It's so cool." And he's just going on and on. I'm like, "It's a minivan." He's like, "Yeah, but it's posh, the leather and this and that and that." And I'm like, "But it's a minivan." And he goes, "Yeah, but think about it. It's really hard to get your mom out of the car because she's tall. It's hard to get her out of a car. It's hard to boost her up into the pickup because she's got some. Well, she's had her hips done and now she's getting her knees done. What a mess. Anyways, and she's really tall, so it's hard for him. He's tall and big, but he's getting old, so it's hard for him to help her in and out." He goes, "With the minivan, she can kind of just like, slide right in because it's about the same height as her buttocks, I guess, to just, slide right onto the seat. And so it's easy to get her in and out of the car." I'm like, "Oh, okay, that I'll buy." Don't try to pass it off as a cool car, Pop. It ain't cool. Now, in your 40s and 50s, there's still a few people that have them, maybe. I don't know. Whatever. Buddy of mine, was he 36 now? I taught him when he was in high school, and his wife, they have 2 kids. A couple years ago, he came in with his tail between his legs one day, and I'm like, "What's the matter?" "Well, we did it." I'm like, "Did what?" "We bought a frickin' minivan." I'm like, "Well, of course you did." He's like, "What do you mean?" I'm like, "Well, you've got 2 kids, and you're in your 30s, and minivans are excellent for hauling kids and their paraphernalia around." Okay. Now, do I like it? Nope. Did I drive one? Yep. Was it cool for hauling their crap around? I won't say it was cool. It was very utilitarian for hauling their crap around. All right. As soon as they were a little older, and then like the oldest one got a car, I'm like, "Yeah, that's it. We get rid of the van." I went back to driving something I want to drive. Okay. So, whatever. Okay. What about Camrys, Jay? Ooh, what about them? Well, like everybody drives a Camry. That's right. Everybody drives a freaking Camry. Okay. Why? Because it's a good car. It's cheap. It's whatever. Okay. Whatever. Let's see. Oh, what's another car I could do that would be? Oh, I don't care. Here he goes. Now, check this out. 40, 50, 60, 80, 100, 112, 13, 17, 120. There you go. Hot diggity. There are 120 people in this data set. Isn't that cute? Oh, how exciting for us. Nice. Nice. I have a question for you. Is what people drive dependent on their age? Again, based on this chart, obviously, this made up data I just concocted, obviously. Okay? And the answer is yes. Based on this, it absolutely is. Okay? How do you know that, Jay? Because the probability that you drive a minivan, given that you are in your 30 to 40s, is wildly different from the probability that you drive a minivan, given that you are in your 50 to 60s, for instance. The same percentages would have to apply. It's not a specific number, but they have to be ballpark the same. Okay? So if you think about this here, so we are in our 50s or 60s here. This would be, 34. Nice. So notice that this is 4 out of 34 people that are in their 50s and 60s here drive a minivan. Okay, cool. That's about, was that about 11%? No, come on, Jay. Do your math in your head. I can't tonight. I don't care anymore. 4 divided by 34 is 12% roughly. Nice. Now, what is it for the other folks? Well, it's 20 out of 31. Whoopsie daisy. Hey, that's a lot different. It sure is. It's wildly different. What does that suggest to me? It suggests that they are dependent. But I feel like I can drive. It's America. I can drive whatever I want to drive. You can't tell me no. Of course I can. You can do whatever you want, friend. Knock yourself out. If you want to haul the kids to school in a freaking truck with a ladder rack on the back of it, knock yourself out. I don't care. Throw the kids in the back of the pickup. I don't care how you get them there. Drive them to school. You want to go to the board meeting in your beat up jalopy? Knock yourself out, pal. You can drive whatever you want to drive. Obviously, as long as you can afford it. I guess you can steal it and then drive it and then go to prison. It doesn't matter. The point is that when we look at data, there seems to be a pattern here. Okay? Now, you're like, wait, is this is demographics, Jay? This is literally demographics. Exactly right. Exactly right. So when you start looking at what radio station you listen to, or what demographic does this show reach out to? For instance, there's a show, let's say it's a sports program, and we're the key demographic might be the 18 to 45-year-old men group. Maybe that's the demographic you're shooting for. Well, if that's the demographic you're shooting for, then when you're going to sell ads, you're going to sell stuff that attracts those kind of people to your ad group. Okay, and so you're not going to waste money advertising to 50 and 60-year-old women because they're not watching your show by and large. Okay, again, not to say they can't, they're just probably not. Okay. When I listen to the radio stations I like to listen to, they know who's listening to them. Yes, it's 106.7, it's Charlie, it's always kind of the ones, a lot of those, 105.9, The Brew, some country stations too. But generally speaking, the stations that I listen to, I hear a lot of this stuff. Do you need a divorce for dads? Do you need some Viagra, etc., etc.? Are you bald? Are you whatever? And you're like, Lord have mercy. They're talking to old dudes. Yes, because old dudes are watching those stations, or listening to those stations a lot. Okay, and they know that. That's why they're advertising towards it. Okay, you would not advertise balding stuff on a radio station that catered to teenagers or people in their 20s and 30s or whatever. What's the radio, Jay? Well, whatever. Anyway, you get the point. When you're on the YouTubes and they play something on the YouTubes for you, an ad for you to watch, and you're like, oh, well, I'm watching car videos, and they gave me one for O'Reilly Auto Parts. Whoa, that was a tough one, Giggles. All right. When they suggest another video that I might be interested in watching, and son of a gun, I am interested in watching it, and it's about something random, and you're like, how did they know? Because everybody else, or a ton of people that watched that first program, watched that other program too. Okay? And so apparently we, think alike. This is what it's all about. Okay? This is how all of our marketing works. This is how everything works like this. Okay? If it was a situation where literally everybody drives a Camry, where when you think about it in terms of age, literally there is no difference in terms of that. It's basically everybody drives it because why? It's cheap and it's a good car, whatever. Okay, cool. In that case, then, if that were the case, you're like, oh, okay, well, that doesn't really scream anything to me. And I can't really make heads or tails of it. If that were a radio program and I needed to advertise, something I need to sell to everybody. So a lot of times I listen to the radio station out of Longview. It's a local station. You'll hear everything on there. Flower shop ad, butcher shop, I don't know, all kinds of stuff. And you're like, why? Because everybody listens to it over there. Okay? And it's just kind of how you do things in a smaller community. And so that's kind of the thing to think about. In other words, there's not going to be a more targeted for this group or more targeted for that group. Okay? Yeah, so that's how this whole business works. You start looking at this and kind of go, oh, so Google follows this, right? They follow and they go, oh, so this guy watches these kind of programs. Awesome. I bet we should suggest that he buy some of these things. Oh, it's like they know me. Well, of course they know you. Of course they do. And they know everybody else who's like you in terms of what you watch and like and are interested in. Of course they do. It's really not that hard. It's creepy as hell, but it's not that hard to figure it out. Okay? And so that is conditional probability. Okay? Now, many years ago, we did one of these where this lady was just yelling out cars. I'd yell out a car like PT Cruiser, and she'd go, "It's an older woman." Oh, okay, cool, whatever. And then she'd yell at some other car, and it's this or it's that. And when it came down to it was a men and women thing this time. And so this was before I changed talking about age primarily, because I think age is actually kind of more interesting now. And I said, look at this. It turns out that based on the data that this class throughout, this was at PCC, there's a higher percentage of women that drive these cars, it looks like, and a higher percentage of men that drive these cars. And it's not close. It's not like it's 50-50 or, 60% of, all the way across for the dudes and 40% all the way across women or whatever. It's nowhere near the same. Okay. What does that tell me? Well, in that case, it would tell me that what you drive is dependent on gender. And this lady freaked out. I'm like, what are you freaking out about? Oh, I could drive whatever I want to drive. I'm like, yes, God bless you. Drive whatever you want to drive. We're saying the data shows that there is a preference for women or men or whoever or different age groups or whatever to certain things. That's all it says. So when you hear the word dependent, doesn't mean you're forced to do something. It doesn't mean there's some evil thing there. It simply means there is a pattern. We're recognizing a pattern. Okay? And this is, again, one of those times where, one of the few times where it's important that we talk about correlation does not equal causation. Frequently, that gets thrown around all the time. It gets thrown around too much to the point where, yeah, sometimes there actually is a thing called causation. Okay. Oh, oh. So you did something stupid and then you got in trouble for it? Yes. See, there is a correlation there, but it is also a causation issue, stupid. Okay. That actually is a thing sometimes. So, but this is one where correlation does not necessarily equal causation. Just because there is a prevalence of, let's say, women that like these cars or whatever it happens to be, and men tend to like these cars, that doesn't mean that you can't go drive whatever the heck you want to drive. Again, it's hard to haul lumber on a PT Cruiser. I'm just saying, okay? It is hard to haul cattle around in a minivan. It's just weird. So I want to get a pickup for that. Okay, cool. But for delivering kids to school or things like that, or hauling the family around, minivans are good. Larger sedans are good. Station wagons are fine. An SUV is good. It's fine. Sure, no problem with that. Prius is not optimal if you have 6 kids or something. A Prius isn't going to get done. But I want to save the environment. Well, okay, but you can't drive a Prius and haul 6 kids around safely. So it's just not going to work. And so, you obviously, different scenarios, again, maybe it's more age situation is more likely. And again, I go back to this. I asked the lady, I said, let me ask you a question. If I told you I saw a truck driving down the street with a lumber rack full of lumber, pulling a trailer with a skid loader on the back of it at, I don't know, 10 in the morning, just going down the road down there, by the lumber yard. Let's keep it by the lumber yard. I said, I got $1 million, says that's a woman driving that. And she's like, oh, you're on. I'll take that bet. And I'm like, well, what do you mean? She's like, well, it's a man. I'm like, wait, what? Well, it is. I'm like, well, I don't know anything. What are you saying? She's like, well, it's most likely. I'm like, so what you're saying is when the money's on the line, you will bet a different way than the way you're talking. And she kind of went, oh. And I'm not, again, not judging. There's just going to be, now, could it be a woman? Sure. Absolutely could have been. Absolutely could have been. Odds are, though, probably isn't. Okay. Probably isn't. Okay. And apparently she knew that because that's what she bet on. Okay. Now, again, it is what it is. Again, you're certainly welcome to bet either way. But when you start thinking about it, I just want you to think about this in the back of your mind. If you would bet money on it, then you truly know what the answer is. Okay? You could say that, I don't think there's any difference between them. But if there was money on the line and you said, well, I'd bet on this way, then you know there's a difference. Okay? Nobody bets on a 50-50 bet. I will bet $1,000 the next flip of the coin is heads. Nobody's going to do that. Nobody's doing that. Bill Gates wouldn't do that. Okay? All right? But if he was betting on a situation where, like he had a pretty good knowledge of what was going to happen, whatever, he might bet on that. Okay? Here's the odds-on favorite to win the race. Okay, you'll bet on that. Whatever. You're going to bet on something that's different. You might bet on the dark horse because you want to take a long shot chance to win something. Okay. But no one wants to bet on a 50-50 race. It's boring. Okay? It's awfully boring stuff. Okay? So, kind of keep that in mind. That's what you're going to be doing this week, talking about conditional probability and dependent probability. Again, those two go hand in hand always. Always go hand in hand. Okay? Last thing I want to mention was on that the pair data, for probably getting a pair. I went back and looked at it. There's 2 ways I could think to do it. The other way, my way, I think would actually be cool, but I'm not really feeling it right now. So 52 choose 5, of course, is our denominator. Okay, and we said there's 13 choose 1 because there's 13 there's 13 ways you could play the game. Okay, so there's 13 cards. You can get a pair of 2s, a pair of 3s, a pair of 4s, etc., etc., etc. So there's 13 ways to do that. Okay, And then, of course, there are four, like for instance, there's 4 6s. Okay, there's 4 6s. You're going to choose 2 of them. Okay, or there's 4 4s, and you're going to choose 2 of them, whatever it is. Okay, and then the next part was the part that I screwed up. So the 12 choose 3. The other numbers. Okay, what do I mean by that? Well, the other numbers are, what are they? Well, they're the other numbers besides the 6s. You with me? So we were picking, let's say, 6s here. There are 12 other numbers, kings, jacks, etc. We're going to pick 3 of those guys. Okay, but we must pick 3 of those guys. All right. So when we say this, we're not going through there, and we don't want to have the chance of, we're not going to do 48 choose 3, because if we did 48 choose 3 the way I was starting to do it the other night, that means I could have ended up with actually a full house, because I could have had a pair and then 3 matches. I could end up with 2 pairs. Either of those would have been a problem. Okay. So I can't do that. And so, but what I could have done is I could have gone through and done it my way, and then subtracted off the probability of a full house and the probability of 2 pairs. I would have gotten there eventually. Okay. But I didn't take that into account. And then this one, 4 choose 1 times 4 choose 1 times 4 choose 1. Now, why is that? Because there's 4 suits. Okay. And so for each of these 3 cards, they could have been in any of the suits. So for instance, let's say one of the cards you chose was a 7. Well, that 7 could have been a 7 of clubs, 7 of diamonds, or a 7 of hearts. Hence, the 4 choose 1, this guy right here. And the other one that you picked, again, let's say I picked 6s over here. My 2 pairs were 6s, okay? And then say the second one I picked was a 9. Well, then that 9 could have come from uh, clubs, spades, diamonds, or hearts, right? And same thing with the ace, right? That could have also come from that. So that's where that came from. That's where that formula came from. So again, I apologize. I think pretty well we could have gotten there doing it this way, but we would have had to do one more step, which I didn't bother to finish because this is just too much. I just didn't want to confuse. All right, well, I already confused everybody, so I want to unconfuse them. This is quite a bit larger than this number up here on top. But if I had to subtract it off the probability of a full house minus the probability of 2 pair, these two should be equal. Should be. Because that's really the only 2 things that they differ in. Okay? But this is the way to do it. And the one on the Wikipedia page shows that as 4 cubed, just in case you're wondering where that came from. Also, I didn't show this in class the other night. 52(5) written that way is equivalent to writing it this way. Okay, it's combinations. Some people write them that way. I don't, because it confuses people. Like, what's going on? Is it a fraction without a fraction bar? What's happening here? Yeah, I don't know. This is the way I choose to write combinations. Okay. Oh, darn it. There's one more thing. Sorry, I lied. There's one more thing. Juniors. Nice. Football. Nice. Nice. What's the probability they get a person who plays football, given that they're a junior? Well, who's in your hat? Juniors are in your hat. How many juniors are there? There are 40 juniors. Don't screw that up. And how many of them play football? 10. Nice. This region in here, those 10 people, what are they? They're juniors and football. Now, some books will write it like this. It'd be the probability of, they would write it this way. They would write juniors intersection football. Is where those 2 circles intersect one another. That's and, because they meet both qualifications. Had I said juniors or football, now of course the answer would be 100, right? There's 100 people that play both. Nice. So that would be juniors or football. This is the union of those sets. You notice I counted, I just went straight across. I said it was 100. Do you see that? I didn't count the 10 twice because it looks stupid to count the 10 twice, right? So if you come back to Excel, the same kind of thing can happen over here if you're not paying attention correctly. Let's bring him over here. Let's get rid of our labels. Boom. Cool. Done. Awesome. What's the probability that a person is a Hyundai driver or has brown hair? Hyundai or brown hair? Now, some people would say it's 39 plus 109. Can you see that? 39 plus 109 over 300. Now, let me draw this picture for you because sometimes it's easier to see on the chart. Sometimes it's easier to see over here. Here are the Hyundai drivers. And there were 39 Hyundai drivers. Nice. And over here are the brown hairs. There are 109 brown hairs. Right on. What's the problem with that? The problem with that, this 109 includes this middle part. The 39 also includes the middle part. Wait, what? Yes, look. Look right there. That's 16 right there. That's 16. That is the intersection. 16 goes in here. Well, what goes in here then? 23. Nice. And what goes in here then? 80, 93. 93. Is there still 109 in here? Yep. And then the rest of the people, that would be, I can't do math, which is good because I teach it. 300 minus 93 minus 16 minus 23 is 168 people out here. Right? So that's the game. So if I asked you, hey, what's the probability the person has brown hair or Kia? By the way, are these mutually exclusive? The answer is no, they're not. So I would take, well, 23 plus 16 plus 93 is, I didn't write that down, did I? 23 plus 16 plus 93 is, that's 132 out of 300 total people. Notice that I didn't count the 16 twice. Now, here's what often happens, though, when I tell you this. People are like, oh, cool. That makes sense, Jay. Cool. It makes sense from the chart. It does. It makes sense when I see this picture right here. It totally does. But if I told you, hey, the probability that you get a person with brown hair is 109 out of 300, and I tell you the probability that a person is a Hyundai driver is 39 out of 300, but I tell you the probability of brown or Hyundai is equal to 132 out of 300. A lot of people get all weirded out by that. They're like, but Jay, when you take this plus this, you get 148 out of 300. You said when I hear or, I add. Well, you're absolutely right. So there's one thing we need to mention. It's not a hard thing, but we do need to mention it. The probability of A or B, you're like, I add. That's right, you do. But you have to be careful. You need to subtract off this guy. Okay? This is always true. Now, but I thought you said just add. Well, I did if they were mutually exclusive. If A and B are mutually exclusive, then the probability of A and B both happening is equal to what? 0. And at that point, it just becomes this right here. So for instance, suppose my two circles did not overlap. Blonde, red, nice. Whatever. Then there would be 56 people, probability of blonde or red is equal to 56 over 356, I guess. Yes? Ta-da! I didn't have to subtract anything off because you don't have any blonde reds. There's no overlap. They're mutually exclusive. Now, by the way, look at the graph. Look in the chart. Look where the blonde and reds are what? They're parallel lines. You see this? That's how I know they're mutually exclusive. Okay. Blondes, Hyundais, not mutually exclusive, right? Now that's not to say. Check it out right there. Check it out. What does that mean? Gray, bald-haired people. Turns out that's mutually exclusive with Chevy on this sample size, right? Because there isn't any overlap between them. That's kind of a weird deal, but there it is. Okay. All right. I think I'm about done yabbering. Hope that helps. Let me know if you need any help.